Hello students, welcome back. In this video we will conclude chapter 5 by going through chapter 5 section 3, Poisson probability distributions. So last section we talked about binomial distributions. Now we are talking about Poisson probabilities, which is another category of discrete probability distributions. So a Poisson probability distribution is a discrete probability distribution that applies to occurrences of some event over a specified interval, and that's what makes it different than other ones. The random variable x is the number of occurrences of the event in an interval. The interval could be time, distance, area, volume, or some other similar unit. You're looking at it over a specified starting point and ending point. The probability of the event occurring x times over a given interval is given by this formula right here. You have the mu raised to the x power multiplied by e to the negative mu divided by x factorial. Remember, e is that natural number that we see in a lot of forms of mathematics, and e is equal to 2.71828. And then mu is going to be the mean number of occurrences of the event in the interval. So the requirements is that the random variable x is the number of occurrences of an event in some interval. Occurrences must be random, independent, and they must be uniformly distributed over the interval being used. So no normal curve. We're looking at a uniform distribution. So the parameters is going to be that the mean is equal to mu, and the standard deviation is going to be the square root of mu. And that's something that we haven't seen yet up to this point. The properties of the distribution is that a particular Poisson distribution is determined only by the mean, and a Poisson distribution has possible x values of 0, 1, 2, with no upper limit. But it must have an x value. It cannot have a negative x value. So let's look at an example. For the 55-year period, there's our interval, since 1960, there were 336 Atlantic hurricanes. Assume the Poisson distribution. Find the mean number of hurricanes per year. So we need to find the probability that and then part B is find the probability that in a randomly selected year, there are exactly 8 hurricanes. We'll get to that in a second, and then there's a part C as well. Let's look at part A. Part A is easy. We just want to know the mean. We have a certain number of hurricanes that occurred over a specified number of years. So what's the average? What's the mean? It's just going to be the 336 divided by 55, which is 6.1. So we're saying that every year, on average, the mean is going to be 6.1. Part B wants to know, what is the probability that in a given year there are exactly 8 hurricanes? Okay, well, that's obviously going to be slightly more than what we expect per year, but clearly you're not going to have 6.1 hurricanes per year. That's just the average. That's just the mean. So the Poisson ratio, we're going to be using that distribution. The formula is given by this right here. So we are saying that mu raised to the x power multiplied by e to the negative mu divided by x factorial is this lovely formula right here, and it gives us a 10.7% chance. So the probability of exactly 8 hurricanes in a given year is 0.107. Let's look at part C. In this 55-year period, there were exactly 5 years with 8 Atlantic hurricanes. How does this actual result compare to the probability found in part B? Okay, so the probability of P of 8 is 0.07 is the likelihood of getting 8 hurricanes in 1 year. In 55 years, the expected number of years with 8 hurricanes is going to be 5.9 years, which means that we expect 5.9 of the 55 years to have had 8 hurricanes exactly. So, and this problem is asking the probability of getting 5 years exactly with 8 hurricanes. So we're pretty much there. This is again is saying that we expect there to be 5.9 years, so between 5 and 6 years, that had exactly 8 hurricanes. Because we're saying around 10% of the total number of years in the interval have 8% or have 8 hurricanes in a year. So the Poisson model appears to work pretty well. We can also have the Poisson distribution approximate a binomial. So the Poisson distribution is sometimes used to approximate the binomial distribution when n is quite large and the probability, or p, is quite small. So one rule of thumb is to use such an approximation when the following two requirements are both satisfied. We have more than 100 trials, and the number of trials times the probability is less than or equal to 10. So if both requirements are satisfied, and we want to use the Poisson distribution as an approximation to the binomial, we need to find a value for mu. We need to find the mean. So the mean is approximated by doing n times p, number of trials, times the probability. So let's do an example. In the main Pick 4 game, you pay 50 cents to select a sequence of 4 numbers, 0 through 9. So you can do 0, 0, 0, 0, 9, 9, 9, 9, or any number in between. So let's say you do 1, 3, 7, 7. If you play this game once every day, find the probability of winning at least once in a year with 365 days in it. So the interval is a day, and placing one day playing once a day results in that we are playing 365 times. So n is 365. There is one winning set of numbers, and there are 10,000 possibilities. 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 2, all the way to 9999. Gives us 10,000 possibilities. So the probability of winning is going to be 1 over 10,000. So with n is 365 and p is 1 over 10,000, the conditions of n is greater than 100 and n times p is less than or equal to 10 are both satisfied. So we can use the Poisson distribution as an approximation to the binomial distribution. We first need the value of mu. So mu is going to be found by doing n times p. So n times p is 0.0365. That would be your mu, your mean. Now that we have the mean, we can proceed with the Poisson distribution equation as shown below. We want the probability that x is at least 1. So we will use a strategy of first finding p of 0, the probability of no wins, and then from there, we'll do the probability of at least 1 win can be found by subtracting the results from 1. So if we get the probability of 0 wins, and then do 1 minus that, that answer is going to be the probability of getting at least 1 win. So we're going to find the probability of getting 0 wins in the whole year. So we have this formula right here. Mu to the x times e to the negative mu divided by x factorial gives us a 0.9642. So there is a 96.42% chance that you will win 0 times during the year. So the probability of winning at least once is going to be the complement of getting 0 victories. So it'll be 1 minus that value. So 1 minus that value gives us 0.0358. So there is a 3.58% chance that if you play the Pick 4 every day for a year, that you will win at least once. Okay, that concludes Chapter 5. Any questions, always email me.